I think this is a good time for us to start. So welcome everyone to our first webinar of spring semester 2024. The first webinar will always be problematic, but this is fine. And we are excited to invite Dr. Xiaozhuo here to give us a talk. Before we start the webinar, I'm going to briefly introduce SZ4D, SZ4Grads, and our webinar series. SZ4D stands for subduction zones in 4 dimensions. We are here to understand the limits and possibilities of predicting subduction zone geohazards. SZ4Grads is under the umbrella of SZ4D. It's collaborative, interdisciplinary, and intercultural network for graduate students and recent graduates studying subduction zone processes. During the webinar, we've got live translated closed captions. You can find a button at the bottom of your screen. Also, please fill out the demographics survey at the start. I'm posting it to the chat. This webinar will be recorded and will be uploaded onto YouTube for you to catch up later. The webinar will be around 45 to 50 minutes. After that, you will have plenty of time to ask questions. You can either raise your hand to speak out or type your questions in the chat. We're excited to invite Dr. Xiaozhuo Wei. He is focusing on seismic study of the Hawaiian volcanoes, and Dr. Wei is currently a Bars Foundation postdoc fellow at Caltech. He graduated last year from University of Rhode Island. He received his master's degree in Chinese Academy of Sciences and also bachelor's degree of geophysics in Peking University. Thank you, and we can all get started.
Hi, everybody. I'm Xiaozhuo Wei. Thank you for the great chance to be invited to give a webinar at SZ4D staff. My topic today as the kickoff, maybe a little bit far away from the subduction zone, is actually focusing on Hawaii. So my title is Ambient Noise Cross-Correlation Study on the Island of Hawaii, promoted by the 2018 kilowave eruption, from vertical velocity discontinuities to lateral velocity variations. My main collaborator are my supervisor, Yang Shen, PhD supervisor, and Julia Morgan from Rice University. And the work here has been published 2 years ago and last year. Yeah, so time flies. Yeah. So as we all know that ambient noise cross-correlation is a very powerful tool since being invented. So from it, we can get the empirical green functions, which is actually really accurate, more or less, accurate approximation of the real green function. So the basic idea is that this method is more or less source-free. We don't need to depend on any earthquakes to monitor. To get impulse response between any 2 stations. So you just input some random, not random actually, but it looks like random ambient noise, and you do this cross correlation, and then after getting the time derivatives, you actually get the green function between the 2 sides. So everything now seems great. It's a really good method, and everybody right now is using it. For example, it's a really, really good tool to imagine the subsurface structures, shallow structures. So on the left-hand side is one of its early attempts in the Southern California region. So where you can see those low velocity basins and offshore region were really characterized, and those high velocity mountains were also imagined. At the similar time, the method was really quickly carried to imagine volcano. So this is Reunion Island. So where using a few stations, they can start to see some shallow magma chamber with 10% velocity reduction. But still, although I'm speaking really highly of this method, this so-called noise-free is still not purely noise-free. So it actually relies on not the earthquake source, but the other environmental sources as the microseisms and maybe the wind. So still it is biased by the uneven distribution of the sources. And also, in particular area, you may have local noise sources. These two things will prevent you get the real green function. Your empirical green function got from the ambient noise cross correlation actually cannot approximate the green function accurately. So this is one case proposed by Zhong Wenzhan in 2010. So where you see from green function perspective, that's already been nice enough. You see the surface wave on two sides, although their frequency are different. But if you look at more closely, you will find there are actual wiggles. So they seems to have a consistent move out. So it means that it's physical, not pure noise. And then when you trace where are those additional wiggles come from, it can be found it's either from a local mine, which produces a blast, this kind of man-made noises, or it's coming from a local plateau where the wind was blocked by the plateau, create a kind of void of noise. So which essentially is also extra noise. So giving you this kind of precursors. So this is the noise still an issue here. And other than the noise, the frequency, the noise distribution, the frequency bandwidth of the noise is another big issue. So as I mentioned earlier, a lot of this method rely on the microseismics, and the microseismics have a more or less limited frequency band from like 0.1 hertz or 0.052 hertz all the way to like 2 or 5 hertz. So you do not have really high frequency signal. So this could be an issue for local small scale studies. But it's right, but the frequency content is a little bit tricky here. So compared with teleseismic events, actually ambient noise like 2.5 hertz can be a high frequency than the teleseismic events. But compared with local like earthquakes, so it's actually not high enough. So then in the end, for global study, ambient noise can basically reproduce all kind of phases, surface wave, body wave. But for local studies, the phases, the wave types phases can be an issue. It only have surface wave during the majority of time, not the body wave signal. And then I'm listing some of the papers, some of the like milestone papers for ambient noise study, where it includes like the very beginning, the surface wave. This is the very beginning, like 2005. You have the science paper, which has been, just like I said, it's a really popular method. So it has been referred, of 500 times from 10 years ago, no, 20 years ago, almost 20 years ago. And then the first study to reveal body wave was like the same year actually, but right now only be cited 400 times. And then when you move on to deeper part, like you don't want typical body, random body wave, but you want the body wave reflecting at the bottom of the crust. So that, first of all, it was published really late, like not really, but 5 years after we know the ambient noise method. But then it only like cited, 200 times. So basically, you can see there's a decreasing trend of citation from surface wave to body wave, and also a publication date delay from the surface wave to body wave. Sorry. Yeah. So here I'm showing some of the like a more 2D figure to show the limitation of the body waves from the in the regional scale, like 1 to 100 kilometer from the ambient noise study. So basically, first of all, the P wave are relatively easier to find. So where a lot of study like Nakata 2015, 16 have and also rocks, the very first one, rocks 2005, they were all able to find this P wave short distance, like 10 kilometers, the diving wave. So basically goes down and it goes up. Yeah, it's to maximum of 10 kilometers. And then with the poly study in 2012, they found the P and P phase, so which is the P wave reflected at the Moho, from like 100 kilometer, 110 kilometer, So 130, 130, So basically, P wave are more easier to find, but there is a big gap here between like 10 kilometer all the way to 100 kilometer, which is corresponding to the crustal reflectors. We don't see them, the body wave. They never go that deep. And then for the S wave, it's even more rare, partially because the S wave, because surface wave is so easy to find, and then S wave is not, it's traveling, with a speed more or less close to surface wave. So the only study like the short, or you say shortest distance to find S wave, to my knowledge, was like 100 kilometer. Like Jan and Polly, they find as a SMS phase, which is the S wave post-critical reflected at the Moho boundary from 100 kilometer. And we don't have a lot of the S wave from like in the regional or short distance from ambient cross correlation. And then, so my target region was the island of Hawaii. Somehow I chose this region for the ambient noise body wave study. It's because this is in the middle of the ocean. So supposedly we should have omnidirectional noise source distribution, which will help the green function to empirical green function to approximate the real green function. On the other hand, the island of Hawaii is really dynamic as a volcano, with it's our island with volcano. So for example, like from a geological perspective, the rift zones, they were not fixed at one point. They were migrating. Some were saying it was migrating from like this rift zone, for example, Mauna Loa. Then from Ninole rift zone migrates to current southwest rift zone. But some were arguing that the blue line should be the old rift zone. It was migrating with a shorter distance. And they were predicting if currently the east rift zone of Hawaii will also migrate to somewhere in the future. So that's one thing. The second thing is actually the 2018 Kilauea eruption. So that's the largest eruption of all Hawaiian volcanoes during the modern human history. So you see the eruption started with magma from beneath the caldera and pumping all the way towards the east lower rift zone. And then they comes out at like nearly 20 watts and pouring lava in a vast area and destroy a lot of infrastructures and people's home, cause some really tremendous hazard. And then there's a chronicle of everything. So basically at the same time, because so much lava was extracted from the volcano system, so the caldera at the summit start to collapse. So then 20, I forgot how many, but there are 10,000s of caldera collapse events happen. So we'll see the topography basically drops of 100 meters. So this gives us a very great chance to look into the details of the Hawaii volcanoes Kilauea pumping system. So and also there are some mineral debates of the formation of the Hawaiian Pro-Simon chain. So we know that's a really long chain formed by Hawaii. It's a classical textbook chain. So it starts from Russian and all the way Pacific, then go to Hawaii. So two member models here. So the first one is the magmatic underplating, and the second one is volcanic loading. So the volcanic loading is really easy to understand. It's basically you have ocean plate, and then you have volcano eruptions. So the eruption will just the new lava will just penetrate the old plate and erupted and accumulated above it, and then form a big island, volcanoes, and then those weights will bend your plate and give us subsidence, and you can mapping it with some gravity anomaly kind of thing. But the other magmatic underplating is more like not as straightforward. It's just when the plume goes up, there are some hot materials will just be kept under the plate, the old plate, and then this hot material will give some buoyancy to the plate, and then cause it to uplift. Yeah. So in the end, the two models can both explain more or less the topography you see along the Simon chain. Yeah, but their mechanism are different. So, but they all predict for the upper. If we are from the point of island of Hawaii, the upper crust should be volcanoclastics and eruptive basalts, and the middle crust should be dikes. The lower crust should be gabbros. So their main difference is not at the top, but at the bottom. So this is all the stations I used for this study. They were basically coming from Hawaii permanent stations, HVO permanent stations, Hawaii Volcano Observatory, and then they come from the Pacific Tsunami Warning Center, and finally one station coming from the GSN Global Seismic Network, where their distribution is not very great. So you see there are tons of stations near these two volcanoes, Kilauea, which is the red circle, and then Mauna Loa, which is the big one, but really few in the northern part of the island because there are no active, volcanoes. And the right-hand side is just a 1D velocity model commonly used for studies in Hawaii, which consists of upper crust, mid crust, and lower crust. And you may have some crust mantle transition zones, then you have the mantle lithosphere. And they are predicting two kind of interfaces, or three, or four. I mean, Moho is a little bit complicated, but two in the crust, like the one separate upper and mid, and then the one separate mid and lower. So I will refer them to V, which is the volcanic basement, and then to D, discontinuity. So then I extract the Green function basically it's ambient noise cross correlation. So you cross correlate them, then you take the time derivatives and reverse the polarity. And then you can see basically that's filtered between 0.1 to 0.4 hertz. That's relatively lower frequency and more close to the microseismons. So you see the data is quite consistent and quite clear. You see the relative move out on the vertical component of different years. Yeah. Beautiful, but not unexpected. And then we move to a little bit higher frequency, 0.4 to 1 hertz. And then at the very beginning of the years from 2012, it seems a little messy, but you can still trace basically a move out according to the surface wave speed. But there's a huge difference between the waveform with respect to this eruption. So still, I mean, even until 2018 April before the eruption, still as messy as before. But then you see the waveform become obviously sharpened after the eruption and persistent all the years. And particularly, you see there's some early arrival at the very beginning, I mean, left-hand side of all these figures, which seems to travel at the speed of P wave, 6 kilometers per second. So it's really exciting to see that. Then that's an even more closer comparison, which is the stack of all the waves before the eruption and after the eruption. So just as I said and showed, the surface waves are really consistent. I mean, the lower frequency, but then when you move to higher frequency, you see there's a big difference, like this clear move out of body wave. So then we were wondering what's going on, why we have a really big, sharp velocity, a waveform change. So one simple way to understand this is through a source search. Like we want to know where are the waves coming from, because we see it's really, really noisy for the relatively high frequency, 0.2 1 hertz. So we were suspecting if there's some extra noise actually contaminating all those green functions. So the research is performed in this way. If we assume there is a source at certain point, the way it will generate some seismic wave arrive at the two stations at different time. But what will show up in the cross correlation is the time difference between the source to the two stations. For example, if the source is there, station 1 and station 2 are there. So they travel this Klein line all the way to those two stations. But then the difference between the same signal on the two stations is related to this ride distance d. And then we can project we can predict the arrival time of this spurious arrival according to the time, like t equals d divided by v. V is like assume the travel time, travel speed of the wave. For here, we assume it should be like surface wave because that's most pronounced, typical wave type, in the ambient cross correlation. So following this way, we do a grid search in our whole study area, whole island. So where you can see the color, the heat map is where we show the noise relative concentration on the island. And then because the waveform are the same for the surface wave part, 0.1 to 0.4 hertz, so don't see big changes. They basically are the same. The dominant source is coming from the eastern side of the island. Maybe you have wind or cross shoreline, stronger wave. But then you see there's a really concentrated source before the eruption at 0.4 to 1 hertz. That's basically where kiloVI is located. And after the eruption, you cannot see the source. The source don't exist at all. And the source is actually very, very consistent and have strong energy. So when you plot all the different maps with the same color bar, you can see this source is dominating all the color bars. And compare with before the eruption, after eruption have really little source energy, from the ambient noise. Yeah, so which means this is all the noisy waveform before the eruption at 0.4 to 1 hertz was dominated by the spurious arrival produced by the noise source. And then in situ, we can also measure the noise source level right at the kiloVI volcano. Yeah, so we basically take we measure the average the amplitude on the vertical component of the seismometers near the SMIT for every single minute and average them in different years, where we can see 0.1 to 0.4 hertz is the blue crosses. So it's actually higher level, like around larger than 1 millimeter per second. So and then for 0.4 to 1 hertz, it was comparable but a little bit weaker. And then you observe a really obvious noise level drop with respect to this eruption, and the data become very consistently no amplitude after the eruption at a higher frequency band and persist for 1 or 2 years. So that's basically is telling us, yes, exactly what the noise source heat map is telling us, that the noise level at the kiloVI was dropping greatly, with respect to this eruption. And one interesting thing is that because, like what I mentioned, the microseismo was actually more close to the lower frequency band, so 0.1 to 0.4 hertz. So the amplitude of that frequency band is actually higher than our high frequency, band. But then after cross correlation, you actually found the noise source is more strong for this one at this high frequency band, which indicates this noise source is really a consistent point-like noise source. So cross correlation will enhance the signal ratio greatly compared to this kind of low signal ratio diffusive noise source. Yeah. So actually, this noise source corresponds to the previous study of tremors, indicating the lava lake, which was active before the eruption at kiloVI summit, is keeping producing tremors. And of course, it's gone because after the eruption, the caldera collapsed, the lava lake was drained. So there's no more fresh lava to produce this kind of train. And then after getting really understand why we start to have P wave after the eruption, we take one step further to understand what those P wave means. So the P wave on the raw data was on the panel B, where you can see the wave move out, but it's a little bit hard to see them really. So I've been stacked them, so that's which is very straightforward. And then basically I can solve there are 3 wave trains. One is more like a line before 20 kilometers, and then 2 wave packets between 30 to 60. And then with hand pick, I can trace the local minimum, and then local maximum, basically pick the arrival time. I benchmark my arrival time with the prediction of different reflections in the upper crust, mid crust, and lower crust. Yeah, in the figure upper left. Yeah. So where you see there are like direct arrival, then it will hit at the bottom of the upper crust, become post-critical PVP phase, one-time reflection. And then it can, the distance increases, you can have deeper penetration. It will have a post-critical reflection at the bottom of the mid crust. And then at Moho, still the wave post-critical reflected at the bottom of upper crust can go back to the surface and then back again to the upper crust and back to the surface, receive the best station. So that's a multiple. So you also have multiple PVP twice at the bottom of the upper crust, and then bottom of, a multiple of PDP. So twice at the bottom of the mid crust. And then I benchmark my travel time with the arrival time. So where we can see basically the most obviously there's a gap between my hand peaks. There's a phase shift. So that's corresponding to the transition from PVP to PDP. And then there was also at the same time, there's a sharp emergence, not sharp, but kind of emergence of new phase, which may corresponding to the PVP phase, PVP2 phase, so the multiple of PVP. Yeah. But I don't know when exactly this transition between direct arrival and the one-time post-critical arrival happened. Yeah, I just marked them there. And compare, this is my observation, and I can benchmark it with a residual function study, also on Hawaii. So they used the only global seismic network station. So they were also able to identify the 3 green lines. So the PVS, PDS, and PMS. So basically the S wave converted at the 1, 2, 3, the 3 different interfaces. Yeah. So which is exciting that the P-wave carries information about the discontinuities beneath the island. But a minor issue is the post-critical reflection is not like typical reflection. It has some phase shift, and we were tracing the local minimum and maximum. So you have to correct for this phase shift to get the real arrival time. So in the end, we were getting the arrival time correct. The raw peaks were on the left, and we get the real arrival time on the right. It really fits well with the prediction of the from the model, but then you still see there are some gaps, particularly for the PDP2 phase. So the multiples of PDP, there's some white area. And then with some trial and error, we can manually adjust our model. So in the end, we're having a new model that visually fits the arrival times better than the original HG50. Which we take it as our final model. So compare with the HG50 input model. So our new model have 8% velocity reduction in the upper crust, 5% in the middle crust, and 5% in the lower crust. And then we deepen the upper crust by 0.2 kilometer. Yeah. In order to keep the middle crust same thickness, I also I reduced the lower crust by 0.2 kilometer. Although this may not be actually required by the data. And then we basically can compare, overall this model with some existing models from active source array and also receive function. So basically, yeah, there's the similar idea that 3 layers beneath the island. Yeah. And then in the finally we can map, back to the figure where the phase exists with this different distance. And then our new studies here so fills a big gap between the P wave reflected at Moho and then the direct arrival in a shorter distance within 10 kilometers. So we basically fill the gap of tens of kilometers that now is powerful enough to also imagine intrastructural reflectors. Yeah. So basically, this scenario also sheds some light on the how to extract a body wave from green functions robustly. So the body wave is actually in the green functions, but maybe they are coming from the same source as the surface wave, maybe ocean macroseisms. But the body waves are very weak. So they are buried by large amplitude surface wave or other noisy signals. And then if you can find a way to remove those signals, for example, like this case, the Mother Nature just destroyed the lava lake. And then we can get the body wave we want. And then there's also a future to maybe use this kind of body wave to do a virtual environmental friendly wide angle reflection. This is a huge issue for region, for example, California. California has never been allowing any active source array ship to go into its shoreline after like 70s or 80s. So how can you do active source array without an active source array ship? So maybe that's the way you put a seismometer as a virtual source. Yeah. And then geologically, we saw the reflectors is not concentrating in one area. So it's actually widespread across the whole island. So which actually led us to favor that the island is more or less uniformly formed. So it's have like this 3-layered is quite widespread beneath the whole island rather than beneath particular volcano. This was more or less against an earlier study, which was highlighting that the majority of the island is actually formed by extrusive materials rather than intrusive. But because we see this PDP, which is the reflector at the top of the intrusive middle crust. So we want to argue that this crust this mid crust may be persuasive, widespread beneath the island. So the intrusion happened a lot of places. This is our final tectonic model where we can add two discontinuities to the big picture, but for the deeper part, we cannot constrain them in this study. And another potential for the ambient noise is that because the body wave can go so deep, like 7 kilometer, 6 kilometer. So this could be important to imagine the magma chamber of Mauna Loa. So Mauna Loa is a 4 kilometer tall volcano, but the magma chamber is 5 kilometer beneath the surface. And in last year, 2022, yeah, close to 2023, yeah. So we have a massive eruption of Mauna Loa. So the lava flow from the top all the way to the bottom. You have all new rift zones, which highlight the importance of monitoring, those big volcanoes. And then we take one step further. We already have the better signals ratio after the eruption. And then we want to do some more routinely ambient noise tomography, which uses the Rayleigh wave. So, but there were some attempts, but personally, I won't think they are really great. They are yielding really great results, partially because the trimmer was contaminating the ambient noise cross-correlation function. So in the end, it's hard for people to extract a very consistent and reliable dispersion from those measurements. So because I know the signals ratio getting better after the eruption, so they are my backbone data site. And then I also find all the stations at that time available on the island of Hawaii from 1916 to 2029. Sorry, 2019. Yeah. So yeah, just to add in to add, to also put input this study to get more data. But I didn't use the stations during the eruption because they are generally noisy. So in the end, that's my empirical green function of all the stations. So where you can see low frequency, there is no problem, and higher frequency, you start to see something different. There seems the wave train, they bifurcates into two trains, and then it's also the same thing when you go for a little bit higher frequency. So that's actually indicates the relative here we have is not only fundamental mode, but also higher mode. This is great because two modes have different information. They can help us to constrain the same structure. But on the other hand, this gives an extra problem because we need to do this mode separation. The modes are separated. Like for example, the modes are definitely separated, like say 60 kilometers at 0.2 to 0.3 hertz. You see there are two wave trains, but around 40 kilometers, they are actually one wave train. The interference with each other. So we have to remove it in order to accurately measure the travel time of the really surface wave. So what we're proposing is really easy. So we know that the radio wave have elliptical polarization, so which we can use Hilbert transformation to relate the vertical component to its radial component. And then because the different mode have at different frequency have totally different ellipticity. So if we can input some crude value calculated from 1D model, and we plug in the equation, then we can do the separation, basically to extract the fundamental. To use the vertical component and the Hilbert transformed horizontal component to get only the fundamental mode and the higher mode vertical component information. Yes. So this is an example of the mode separation and dispersion peak. So basically, after mode separate, we basically take the raw data and then we do the mode separation. So where you can see, for example, this one, the raw data shows very strong interference where the interference was constructively interfered around 0.25 hertz. So where the two waves merge into one, but destructively interference at 0.3 seconds. Hertz. So the two wave trains separated. And of course, if you move on, there is no more interference. It just become two. And then after the mode separation, where we can see we first do it for the fundamental mode because fundamental mode is very persuasive. Then we see the fundamental mode become very clear. This kind of interference was almost all removed, and we can pick the arrival time according to a reference dispersion from the 1D model, and then we can extract from the raw data this fundamental mode energy, which left us the first overtone, which is also matching the prediction from the same 1D model here. So basically, we get the dispersion curves for the station pair of the two modes, and then we make it automatically. We can do it for every single station pair, and which bring us to have a figure of all the dispersion measurements. So where you see different color corresponding to different group speed, and then of different modes, the fundamental and the first overtone, and different frequency. So higher frequency, higher speed, lower frequency, lower speed. And then you start more or less to see some systematic pattern where a lot of red appear between the volcanoes and some intermediate velocity in the north, and there's some high velocities in here and there. Then we move on to do a very traditional, mature like surface wave tomography, which was exactly mirroring what I was saying. Low velocity in the north between the volcanoes, and high velocity in the rift zones, especially the Kilauea East rift zone. Yeah, and then we can get some estimation of the resolution. So I won't say it's great, but some of the region between the volcanoes and in the East rift zone is still resolvable. And then that's the same thing, but for the higher mode. You can see basically the structure looks similar between the volcanoes, low velocity, and high velocity along the rift zone. So because we know that different mode, different frequency are sensitive to different the shear wave at different depths. So these are the two examples. So we can do an inversion for 3D shear wave model, and the model looks like this. So basically, we are just like the surface wave dispersion showed. We have low velocity beneath the between the volcanoes at different depths, and then the velocity in the northern part was not that low until like 0.1 kilometer to 3 kilometer, but we always have this high velocity along the rift zones. So this is a more example to showing some of the the shear wave structure. So on the left hand side is their fitting to the observation of surface wave, and the left here is the points in the rift zone. So they are more or less high speed, and you see they start to go into the region of the pillow basalt at around like less than 500 meters, and then they go into the zone of the basaltic dikes at around 2 kilometers, so which indicates they are more or less fits their geological siting of intrusive rift zones. So you have intrusions that really close to surface depths. But then for some of the curves outside of the rift zones, you see they didn't go into the like more or less high speed intrusive material region until like 1 kilometer. And some of the points are characterized particularly by the shallow 100-meter low velocity structures, which is required by the higher mode data. If we remove the higher mode data, you will not see this kind of sharp drop of the velocity. But then this prediction from the fundamental mode actually cannot fit the higher mode data. So overall, we are arguing the higher mode is important, but although it's also hard to measure, yeah. But they are important for us to better understand the underground structures. And finally, we compare our shear wave model with some existing models, and these two are P-wave models. So where we see at the shallow depths, they also imagine similar thing, low velocity between the two volcanoes and high velocity along the rifts, which is not surprising. And particularly, we see that our right hand side, near close to 3 kilometers, we see there is a trend of high velocity basically is going south. It's not along the rift, but going south, which corresponding to some existing study. So you see this going south trend and this south trend. Especially this one, they were arguing that's a relic rift zone, which was there like 10 million years ago, but migrated to the western one, which is its current location. So, and then we found there's some shallow structures, and particularly, it's very interesting that between the volcanoes, we know there are faults, there are lava flows, which is not surprising. But this one is particularly looks interesting to me because they are in the north of the current rift zone, and currently the rift zone basically erupts to the south. But that's not the case in the past. So the largest eruption called Eliyahu eruption of Kilauea, which happened like 300 years ago, which lasted for 50 years. produces very massive eruption towards the northeastern coast of Kilauea. So it actually coincides with this low velocity zone. So which also argues even this region could be some ancient eruptions, low velocity extrusive materials. And then for the high velocity rift zone, it's a little because we are imagining the shallow parts rather than deeper parts. So the deeper parts is really easy to understand. Is that you have active magma chamber, and then the magma chamber was sitting there in the middle crust, and then or the bottom of the upper crust. With the time progresses, it will cool down, but it will form like solidified rocks surrounding it. So you have the more pronounced deeper part of the high velocity. But we were arguing that when you form eruptions along the rift zone, you can also have some residual magma inside the eruption conduit to the surface, and after time they will also solidify. So in the end, you should have high velocity not only near the magma chamber but all the way to the surface. So which can be explained by our observation here. And there was another issue, more or less a paradox, is that we only see a very strong rift zone in the Kilauea one. But the issue is Mauna Loa was actually older. I mean, it must have erupted more times than Kilauea in the geological timescale. But then why we cannot see such a strong rift zone from Mauna Loa? We tested with the checker, resolution test. It shouldn't be the station coverage because you see this is really strong. But if you have similar thing, you should definitely imagine them from Mauna Loa. So one explanation we propose is that because although Mauna Loa is older, but the rift zone may not be the case because the rift zone have some migrations from the south to the southwest. So actually, this rift zone here could be even younger than Kilauea ones. Especially consider Mauna Loa right now is not erupting as frequent as Kilauea. So we solve it by saying the older volcano is having a younger and less mature rift zone. So this is to reconcile our observation, the differences between the two volcanoes. So in the end, we are the two studies, when we put them together, they give us a comprehensive understanding of the island of Hawaii. We see strong temporal variations in the empirical green functions. We have P waves only after the eruptions, and then that's revealing three crustal layers. Could be the shallow ones, eruptive basalts, and then dikes, and then gabbros. And then we move on to rainy wave signal. We imagine strong lateral variations of the structures. We have high velocity intrusive rift zones for the volcanoes and low velocity volcano flanks and fault zones, which may give you the extrusive porous lava flow and then the fault debris. And the Mauna Loa shows a very different structure compared with Kilauea, which could be explained by the scenario of a major rift zone reconfiguration happened to Mauna Loa, particularly southwest rift zone. Yeah. So overall, I want to thank the NSF for the financial support, and I want to thank the people who maintain the permanent network and deploy, recover the temporary seismic stations, and their efforts to make the data publicly available. And I want to thank Fan Qilin and Jamie Fennell at University of Utah for providing their newly deployed nodal seismic data. And we thank Kevin Bryan at University of Rhode Island to help computing, particularly the empirical green functions. Correlation are really time consuming to calculate. And thank you all guys for listening.
Thank you so much. We got one question here I think I'm going to read it out because for further recordings, you have to like know the question. So this is a question from Charles. Hi, Dr. Wei. Can you expand a little bit more on the presence and causes of asymmetry in your EGFs? Negative versus positive lags before stacking, I would assume this is an issue, but I'm wondering how, if you need to worry about that.
So I actually don't have a figure here. Because in my study I basically ignored this asymmetry. I just fold them and stack them into one, and then you only have time from 0 to like 100 seconds. But you can see some of the asymmetry from like my noise model. For example, for the low frequency, you see the energy is systematically stronger on the right-hand side of the panel, which is the eastern side. That's because the two legs, they do not have the same energy. So like if you have two stations, my two hands, so the stations so the left hand side, so the station receiver is on the left, will have larger amplitude. The station on the right will record weaker amplitude. So that will produce back project the energy to the right hand side. So yeah, that could be a real issue of the asymmetry, but I don't think that's an issue for my study here, and I really didn't consider it.
I'm not an expert on this, but I also have a very simple question, or even more questions about it, if nobody is going to ask questions. So, for the anomaly you observe here, in the frequency band of 0.1 to 0.4 hertz, this is also a kind of anomaly. Is there any interpretations about that?
So one way to think, I really don't have what interpretations, but I do have some speculations. So one way, so first of all, the wind blowing to Hawaii is basically always coming from the northeast. So then you are not expecting you have strong energy in the southwest direction, because that's not the wave, that's not the direction of the wind, and the wind will blow waves to the shoreline, and when the waves splash at the shoreline, they give you the ambient noise. So I'm expecting it makes sense to have my right hand side stronger than my left hand side, particularly the southwest corner is really blue. I mean, that makes sense. But then why particularly is in my east corner? I don't know. Somebody was telling me that that's because the shores are different. They were saying when they were at the beaches, they found the shoreline in the southeastern part is more like cross compared with maybe smoother sand or smoother rocks in other region. But I really doubt, because a few beach cannot be, it can be biased. And then yeah, I didn't do a very systematic study, but yeah, that's my speculation, but I don't exactly have the answer.
Sounds interesting. Can I ask another quick question? Very
Yeah,
quick.
yeah,
I
go ahead.
promise. So in the background, you mentioned the potential migration of two places. And can you infer the real direction of the migration from your velocity tomography? I mean, yeah, I remember you mentioned two different directions of the potential.
Yeah. So I honestly I cannot, because first of all, they were arguing, they were migrating like for example, look at the right hand side. So the blue one is one proposed model, and the right one is the other. But you see, they all share the upper parts. So it's only they diverges to the, I mean, if it diverges to the southwest or southeast. So my study only go to 3 kilometers depth beneath the surface. So and the resolution is not good there. So I really don't see how, which direction it really, bends to. But if you want me to really say one, I would favor the one goes to the right one, because in my model it seems go that way. But that's definitely what I don't want to interpret. And on the other hand, I want to say maybe the two models are both correct, because it's not necessarily your migration will only happen once. It can happen once between the red and the blue, and then another time between the blue and the black. So that could be a way to reconcile those models, but still, because one thing hard for this is that repeatedly eruption covers the old region. So right now you can only see everything geophysically. You cannot see on the surface. So geologists are not very happy about this. Volcanologists, yeah. And some of the methods of the geophysical have really have some uncertainties. So which causes some of the arguments. Yes.
Sounds great. We have another question from Hal saying that, can you locate the depth of the noise source before eruption?
Depth. Oh, no, I cannot. Because right now I'm assuming they are surfacial source, and they basically give out surface wave. So in my case, that was a 2D problem. I do not have depth constraint. But there are other people who have depth constraint. They were doing different methods, like, of course, as you can imagine, in order to resolve the depths, you need stations really nearby, because the depth is not an issue if your stations were 100 meters, kilometers away. So at the regional scale, they were trying to do this kind of thing. Yeah, but personally speaking, I think there are some inconsistency between their results and some of our knowledge for this source. Yeah. I saw another question in the chat. So it also comes from Charles. So in comparing Mauna Loa and Kilauea, aside from just age, wouldn't a simple control on the prevalence and frequency of rifting that is different between the two be the relative differences in the absolute depths of the magma chambers? I'm a little bit confused about this question. Wouldn't be simple. I don't quite understand this question. So you mean, so the magma chambers are different, so the rifting frequency is different? Is that what you are trying to argue? I mean, yeah, I mean, the depth of the magma chamber of Kilauea is relatively shallower. We actually have two. One is between 3 and 4 kilometers. The other one is between 1 and 2 kilometers. Yeah, but I'm not sure. I mean, this is a little bit tricky because I speculate so first of all, the magma chamber depth is determined by the magma density. So if your magma density is the same, if they're erupting the same kind of lava, then the chamber should be the same. So my speculation is that Kilauea have a shallow one because it is more active. But Mauna Loa is not less active, so there's not enough magma to form a shallow magma chamber. Because I can't imagine if eruption happens, I mean, frequently, you are fueling it with a magma chamber from 5 kilometer depth. That's really deep. So overall, I'm thinking the control factor is the magma supply. So which controls both the magma chamber numbers, depth, and also the rift zone maturity. Because in the end, the rift zone was also filled by the magma chamber. Yeah, I hope that answers your question.
Okay, great. Thank you so much for the brilliant talk. And this is a perfect start of this semester's webinar. And thank you. Bye-bye.
Thank you for inviting.